In this lecture, we're going to talk about loops. So there are a few things that computers are really, really good at, and there are a number of things that they're not very good at, but that's probably a different lecture. One of the things that they're really, really good at is doing the same thing over and over and over again. They never get tired, they never get bored, and so let's learn to use loops. So there are several different kinds of loops, and these are things that are probably taught in some of the really basic classes you might have had. So you might have seen some of this before, although I'm going to sort of assume that you haven't. So the first kind of loop is called a for next loop, and it allows you to process data, variables, instructions, anything that you want to do in a particular order in a particular number of times. So say, for example, you wanted to do something exactly 100 times. Then the for next loop is for you. The number is known ahead of time, though it doesn't have to be hard-coded in there. Something you can detect, like the length of an array or something along those lines. In fact, that's probably the most normal use case you're going to see is however many things there are in a given array or a given list, that's going to be the upper boundary for your for next loop. So let's take a look at one. I think it sort of speaks for itself with respect to the syntax. It's fairly straightforward. This is what a for next loop looks like in pretty much all C-based languages. So this is very portable. There are only going to be minor differences, say if you move over to Java or Objective-C or some other C-based language, JavaScript. But this is pretty much going to be what it looks like, and certainly how it works is the same. So you begin with the for keyword itself, and then within parentheses we have the creation of a variable. This is sort of a dense block of statements here. So we create this variable called I, and we set it to 0. And then we have this semicolon, and the semicolon breaks up the three parts of this for next loop. The second part is the condition that the for loop is looking for as it tries to complete. So in this case, we're saying the completion condition that we're looking for is I is less than 100. So it's basically going to check to see if the condition is true. And as long as it is, then it's going to keep running. And then the second part is the actual incrementer for the loop. So if you sum this up, it's like saying I equals I plus 1. That's what that I plus plus thing is. So it's basically saying we're going to start at 0, and as long as I is less than 100, so it's going to go from 0 to 99, then we're going to execute the code that's down there in that commented section that says code loop here. And then at the terminus of that, that's going to go ahead and do that I plus plus. It's going to increment, and it's going to try it again. So as it goes through, it starts at 0. It checks to see whether or not 0 is less than 100. Of course it is. So it executes whatever's in code loop here, and then it says I plus plus. So now the value of I is 1. Is 1 less than 100? Yes, it is. So it runs the code loop again, runs I plus plus. Now I is 2, and so on. It continues until it reaches 100. And as soon as it gets 100, it checks to see that I is less than 100. Well, 100 is not less than 100. And so that's the end of the loop. And whatever is after that closing brace is what gets executed next. So I have this nice little warning in here. I used to use this slide for my JavaScript students, and ironically, it's probably not ironic, it's interesting that the syntax is identical. Because of implicit typing, I can use the var keyword, so I could literally recycle my slide. But there is a sort of a famous or noteworthy programmer out there that's writing books, and a lot of people consider him influential, and I rather like his work, and I really like his style of programming, especially in JavaScript. He cautions against using this I++, this sort of syntax, and he thinks it's less safe and less readable than I equals I plus 1. So I want to point that out, that there are people out there that think that this is not the way to go. That said, pretty much everybody on the planet does I++, and so he would be in the majority, or excuse me, in the minority. Most people are going to put that I++ in there, and that's the way we've been teaching this for decades. This goes back way, way, way far. I learned it when I was 12, so it's been around for a really long time, because it's been a really long time since I was 12. All right, I wanted to show you something else interesting on the next slide. What if you wanted to count backwards? Well, you can do that. You just start at the the upper bound for your count. Your condition then is I greater than 0, and then you're doing I minus minus, a decrementer instead of an incrementer. So other than that, it's the same thing. So you can count up or you can count down. The key takeaway to this, you can even count in steps if you really want to. You can count by 5s or 2s or 3s or whatever you'd like. But the key takeaway for this is that you know in advance how many times you're going to execute this loop. So that's really the key to the for next loop. Let me show you a different loop, which is useful with collections, and that's the for each loop. So pretty much what you're doing here is you're working with any kind of collection, and collections pretty much all in C# all implement an interface called IEnumerable. That would make a fine test question, by the way. So collections in C# implement IEnumerable, and a for each loop is designed to work on anything that has some sort of iterable quality about it, something that you can iterate over, and that's what IEnumerable is all about. So what's nicer about this is that you automatically get a reference to the current object in the loop, so you don't have to worry about the index, you don't have to worry about square brackets, you don't have to worry about incrementing counters. It's a much easier thing to use. Let me show you an example, and it's a full example so that we have everything in there. We're going to work with a collection. In this case, I've called it test collection, and it's going to be a list of strings. So I've defined it there as the list of strings, just to harken back to our collections lecture, which I literally recorded 2 minutes ago. And so that's what they look like. Remember, we've got the angle brackets that are telling you that this is going to be a type-safe list, and it's going to be of type string. So I can really only put strings in here. If I have a test question that says, why won't this work, and I have a list of strings and I try to stick an integer in there, that's going to fail to compile. And so that's why. The lists are type-safe. You can only put the kind of information in that you're telling it you're going to store. All right, so that's the sort of the setup, and then you can see that I've got testcollection.add, so I'm putting all of these values in here. So I'm putting 4 strings in there. Thunderducks will own you. And then after that, we get into the actual for loop itself. So it looks pretty similar to the other one, the for next loop. It almost looks the same. We start off with the for keyword, and then we go into our parenthesis. So hopefully you're getting used to seeing those. Parenthesis pretty much is always going to enclose any sort of expression that you want to evaluate. And so we're evaluating what goes inside of here, and we're creating a variable called test, and that's one of the important parts of this. Test in, the in keyword here, and then the name of the collection, which is, of course, test collection. So we've got test collection, 4 things in it. It's going to say for test in test collection. And what does that get us? If you look down there inside the curly braces on the line of code there, it says system.console.writeLine test, and that's where we're getting our reference. So that's what's cool about this. We get this reference called test, and you'll note there's no dereferencing going on here. We don't have to go in and get the index. We don't need curly braces. We don't need any of that. It just assigns each item in turn to the variable test, and then you can use it down there in your code block. So that's super nice, really easy to use, and it's probably the weapon of choice for most people whenever they're dealing with a collection. All right, so there are a couple of other kinds of loops, actually 2 left that I really want to cover, maybe 3. But these 2, while and do, these are really almost the same thing. And then we're going to talk about the game loop in Unity. It's an important concept for game developers. So we'll do while and do first. As I mentioned, they're almost the same. And the key takeaway from these is they execute until a condition is met. So the for loop executes a set number of times. The for each loop basically just goes through a collection, and everything in the collection, it works with that. This is actually waiting until something is true or false, until a particular condition is met. And this can be something called an infinite loop. It could potentially run pretty much forever. And back in the old days, that used to be considered a bad thing. It was an error if you created an infinite loop. But now we have infinite loops. They're not really infinite because you can exit them, but we have these sort of coded up as infinite loops. That's how you make a game, and that's normal. But again, it's not an error condition because you can exit the game, and that's under your control. So just as an interesting piece of trivia, the Apple headquarters, their street address is one infinite loop. Pretty neat, right? All right, let's take a look at what these infinite loops, or I guess more specifically, what these do loops look like. These are not going to be infinite loops because they're going to have solid exit conditions on them. So a do loop looks like this, and this is what's funky about the do loop. It starts off with do, which is not really the funky part. And then we've got our curly braces. Hopefully you're getting used to seeing those as well. You've got the code inside that actually makes up the loop. This is the code that gets executed. But here's where it gets interesting. The condition is followed by the while statement. So we've got the while statement and then the condition. And what's interesting about that is it comes after the code is executed. So this is the key takeaway for the do loop. It always executes one time because it evaluates the condition after it runs the code. So you can guarantee that it'll always happen one time, and then it goes and checks to see if the condition is true or false, and then it works from there. If we take a look at the while loop, it looks really similar. So instead of do, the keyword here is while, and it checks the condition up front. So it doesn't check it after, it checks it up front. That's the biggest difference. Curly braces, just like everything else, and then we've got the block of code. So this one is not guaranteed to execute at least once, whereas the do loop is. Other than that, they're really, really similar to one another. All right, and then there's one more loop I want to point out, and that's the Yoda loop, which is a do or do not loop. And of course, I'm kidding. There's no such thing as a Yoda loop. But you'll notice that I actually probably should have put this in the try-catch lecture, because it's do or do not. There is no try. See, there's the catch there. Yeah. Sorry. Okay, let's move on to the game loop. So Unity manages this thing for you called the game loop, and you don't have to worry about it. This is one of the benefits of using an engine like Unity, is it handles those things for you. So a game loop is something that game programmers use. It's pretty much it's not really an infinite loop. It's a loop that runs until you tell it to exit, and there is sort of a difference there. An infinite loop is an error condition where you think you've defined an exit condition, but it's an exit condition that can never be met, and that's usually a bad thing. But what's different about the way game programmers write games versus the way a corporate programmer or an application programmer writes application, or apps if you prefer the term, is game programmers use this loop that's always running, and that's what really gives them the speed of execution that they need. The event-driven model that application programmers use is usually quite a bit slower. So the game loop runs at about 60 frames a second in Unity. It doesn't necessarily run at exactly 60 frames a second. That's what they're shooting for. That's the ideal. But the frame rate is actually going to depend on the speed of the hardware. So if you're running on a really, really cheap processor on maybe an Android device or something like that that's got, sort of substandard, it's a $20 Android tablet, you're probably not going to get 60 frames a second out of it. Whereas if you're running, the highest end processor that you could buy, maybe you went to the Apple store and spent $30,000 and you've got the fastest thing on the planet, you may actually get quite a bit more than 60 frames a second out of that hardware. We usually try to get 60 frames a second because that's a good frame rate for games. We really can see, I think we can see at 60 frames a second, but animation doesn't really fall apart until around 12 to 15. So we have lots of wiggle room for degradation in our animation and things like that. But 60 is just a good number to use. The refresh rate on a lot of monitors is around 60 hertz. So 60 times a second is perfect. So the term here to remember is frame. So that's one iteration of the game loop. So each time a frame runs, that's one iteration of that game loop. Unity has an event system, pretty much everything does, but Unity's events are triggered based on these iterations of that game loop. And these are things that you've seen before. You've seen these in the scripts that we've created so far. For example, start. So start is an event that fires when the game first runs, and it only fires one time. That's one of the things that's different about start. Most of them fire at different times, but over and over again. So for example, update. Update fires every single frame, and that's what it's all about. There are different versions of update. You'd have to go through and read all the documentation on the different things that you can do with update, like fixed update, late update, things like that. There is actually an assignment that challenges you to go find all of those different events and document them so that you have a nice list that you can refer to when you need to. The thing about update, though, is that not all of your code is going to be able to execute in 1/60th of a second. So you really have to be careful. You don't want to put anything really heavy in here that's going to take a long time to compute, or maybe manage a large collection of items. If you do that, then you're going to see a lot of lag in your game. Your game is going to slow down because the frame rate's going to drop because it's waiting for your code to execute. So you kind of have to be a little bit careful with this and bear that in mind. So most of the things that we do, we're just updating some properties, and we don't have a lot of things in our games so far, so doing everything in update is fine. You'll learn a little bit later that you need to use different techniques for more computationally intensive elements. So as I mentioned, there is a writing assignment. I really recommend that you do it, especially if you want to be a Unity programmer for a living. That's the kind of thing that you really need to be exposed to. And I highly recommend that assignment. I'm actually considering making it a requirement, but I haven't done that yet. Look for an announcement on that. If I don't announce it, then it's not a requirement. If I do announce it, then obviously it is. But I think it's really important that you understand the different events that Unity fires. So the next thing I want to cover is I want to branch off a little bit from our events and talk briefly about coroutines, because they're such an important topic, and I really struggle with, should I teach this in the intro class or should I teach it in the advanced class? And I've had students actually ask me in the intro class, when are we going to cover coroutines? And so let's talk about them. I think I'm going to start moving this at least a little bit into the intro class, even though they can be somewhat advanced and a little bit tricky. I think they are such an important technique that we at least need to know what they are and know how to recognize them and hopefully understand how to pick them apart. So let's do that. So this is something that you do sort of as you evolve beyond doing everything in the onUpdate or one of the onUpdate events. You start using coroutines. And coroutines are employed anytime you have something that will run longer than one frame will allow. And a really obvious example is, let's say you want to interact with the internet in some way. Maybe you want to send a high score, or you want to get some data from the internet. And that is a big variable, isn't it? You may not even be connected to the internet, let alone you don't know how long the latency is going to be, and how often do you actually get a response back from a website in 1/60th of a second. So that usually takes a lot longer. So anytime you want to do anything with the internet, you're talking about a coroutine, but it doesn't have to be that. That's just a really obvious example. Let's say you're wanting to get a list of all of the bad guys in your game. Well, if you've got 5 of them, that's no big deal, especially if you've made a pool of your objects, and that's an advanced topic for sure. But what if you have hundreds, or even multiple hundreds, or even thousands? Hopefully it's not thousands, because that would be really hard. I think the only game I've ever seen that has a really, really high number of things to iterate through is Civilization. And you've probably noticed, if you've ever played that game, that the further along you go, when you start getting around the year 2000, those turns start taking longer and longer and longer, don't they? And it's a turn-based game, so you're kind of left wondering, well, why is it taking so much longer? Well, it's because every country on the board has hundreds of things. So they've got all their land units, and they've got all of the improvements on their tiles, and they've got their workers, and they've got their economy going, and there's all that stuff happening. So at the beginning of the game, it's really quick, and at the end of the game, it's really, really slow. And they're just using techniques that we've been talking about, right? They've got a collection of items. They're iterating over the collection using lists and loops just like we've been talking about, and they're responding to various events. And so, it's very, sort of tied into what we're talking about. That is exactly what we're talking about. So as you go through, you have to figure out ways to do these kinds of operations outside of a frame calculation. So again, anytime that you have to run something that will take longer than a 60th of a second, it's time to bust out your coroutines. So you can think of it this way. You're basically telling your program to do as much as you can within the confines of a frame, but don't hold up the execution of the rest of the game. Basically, you're telling it to sort of stick a thumbtack in it. So we'll put a pin in it, come back to it on the next frame, and that's exactly what happens. And you do that there's a special keyword for this called yield, and it pretty much does what you think it does. It says, hey, let's just sort of put a bookmark here, and we'll come back to this computation as soon as the next frame starts. All coroutines have a return type of IEnumerator. So remember, this is an interface, not a type. So anything that falls into that particular interface is fine, although usually you're just going to see IEnumerator as the return type. Don't confuse this with IEnumerable, since we're talking about collections. At least peripherally, the last lecture that I did was collections, and we implemented the IEnumerable interface there. That's not the same thing as IEnumerator. So just realize that they're two different things. That would also make a fine test question, or at least a good distractor. All right, let's take a look at an example. This is taken right out of the Unity documentation. And so let's sort of pick this apart. By and large, this is just a plain old method. There's just a few things in here that are different from any other method that you might write. First and foremost, again, they have to return the IEnumerator interface type. So anything that generates an IEnumerator interface is fine, though you don't usually deal with the return type, at least not directly. And then you have all the normal parts. In this case, we're actually trying to fade something out. So what we're doing is we're manipulating the color of a material, and we're changing it from one color to another color over a series of frames. So you don't want your fade to happen in 1/60th of a second. That would be too fast to see. You want a color to change over time, and you want it to be noticeable. And so you need to do this over multiple frames, and that's what we're doing here. So we're doing a little bit of work, and then we're going to come down to this yield statement. And in this case, it's not really doing anything. It's just yielding. So it says yield return null, and that's fine. So on the next go around, the next frame, it's going to pick up where it left off. So maybe there's 100 steps between the two colors that you want to fade between, and maybe it gets 5 of them done or 10 of them done, and it will take 10 frames to get the work done. So each time a new frame starts, it picks up wherever it left off, and it resumes the computation, and it stops as soon as the frame ends. And so it just keeps going until its work is done, and then that's the end of it. That's the end of the coroutine. So that's what the coroutine method looks like. If you actually want to use it, you have to use a particular method call called start coroutine. And I basically borrowed this example from, again, the Unity documentation, spawn waves, which has nothing to do with fading. But I wanted to point out spawn waves because when you did your intro class, you were required to make a game called Space Shooter. And Space Shooter used a coroutine to generate different waves of opponents. So I recommend that now that you know what some of this stuff is, that you go back and look at that exercise again. I don't require you to go back through it all the way, but it might make sense for you to go back through some of these introductory exercises that you were sort of tossed into in your intro class. Now that you're understanding the context, they might actually make a lot more sense. So the only trick to this is that when we're starting the coroutine, we're passing in a function. Not the name of a function, we're actually passing in the function itself. And I briefly discussed in class, and I know I've mentioned in the functions lecture, the concept of a lambda language. And a lambda language allows you to pass functions as arguments and also take them as return types. And so this is something that's I'm not going to say it's unique to C Sharp, but it is a very hot topic in programming these days. And most of the newer, hipper languages are Lambda languages. So Java's adding the capability. C Sharp can do it. JavaScript, you pretty much can't do anything without doing something with a Lambda. And so all of these different languages are adopting this methodology. So you're going to see it everywhere. Okay, just a couple of points to close up on coroutines. They're a technique. A lot of people think that they're a keyword built into C Sharp, and that's not the case. They're not really even part of C Sharp. If you go look up coroutine on Wikipedia, and I recommend that you do that, you'll get sort of a generic computer science recipe for a coroutine. And in our case, we're talking about a very specific Unity capability centered around the start coroutine method. So they've sort of taken this generic methodology, this generic technique, and they've applied it as a workaround. And a workaround is usually a bad thing. In this case, it's fine. It's the way it should be done. We need a way to process something that will take longer than a frame. So that's really the perfect application of a coroutine. So it's not part of C Sharp, it's actually part of Unity, but it is a generic idea that all programming languages can in one way or another implement if they wanted to. So that's pretty much it for loops, and I know we sort of spun off into events and coroutines, but I think they all sort of go together. Once you start talking about loops, you have to talk about the game loop. The game loop, again, central to pretty much every game platform out there. They all have it. Unity has it. The frameworks like the old Microsoft XNA framework has it. So does the Mono framework that replaces XNA. They all pretty much have the game loop in them. So it's a central concept to game development. And then from there, you need a way to be independent of your frame rate, and coroutines let you do that.